Today what we're gonna do is clustering. So this is the first time we actually the clustering is one of the unsupervised learnings, and everything or all of them that we learned so far is supervised learnings. It's regressions and the classifications. All the method that we discussed so far is part of the supervised learning. Supervised learning is, last time I mentioned, that is whenever we have data set, that data set is the data set consists of input and associate outputs or labels at the same time. So this is the first time we're talking about unsupervised learnings. The first one is clustering. I'm gonna discuss and tell you about what is the clusterings, and here is also is k-means. Probably I'm gonna focus on k-means method. So here, supervised and unsupervised learnings, there's two big categories that we can think of. Is supervised learning is build a model from labeled data set. Like I said, input and associate or corresponding labels from the outputs, right? And on the other hand, on the right side is unsupervised learning, is that we do, it doesn't have to be clustering. Clustering is part of the unsupervised learnings, but it's just focusing on the clustering. It's clustering from unlabeled data set, which means that there is only input available. There is no output. So unlabeled data set means that only input is available. In the pictorial explanation is that here, as you can see, there are two figures, and the only difference is that you can think of there's like kind of two, I'm gonna say groups, because I cannot say clustering, because clustering is kind of specific meanings in machine learning context. So I say there's two groups. The only difference is that here I use different colors. I use different colors, but here I use same colors to represent, which means that here red is probably part of one labels and the other labels. Over there, on the other hand, there's the single colors, right? So we don't know labels. We don't have any labels. That's the biggest difference. And in mathematical expressions, like said, we have x, we have x and y, like that. We don't have y's. Only thing that we can have given data set is inputs. So we call it, over there is classifications, over this clustering. So you can think of it as grouping, partitioning, clusterings, classifications. In plain English, probably we're gonna like pretty much use this, all those terminology in a similar sense, but in the machine learning context, classifications and the clusterings are totally different. Okay, you have to very be careful. Classification is part of supervised learnings. On the other hand, as opposed to clustering, is kind of clustering in unsupervised learnings. Okay, and grouping is, there's no grouping in machine learnings. So I would say classifications, clusterings, both of them are like a grouping, some grouping, but here with the labeled data set. On the other side is with unlabeled data set or without any outputs. So that's the biggest difference. Here, what you can see is that by looking at this, since we visualize, we plot them, it's for us, it's extremely easy. Like there's two, I would say, groups, and we can do kind of grouping. So we call it clusterings. But think about perspective point, the computer point of view. Say this is x of 1 and x of 2. So X of 1, X of 2, we're gonna have a bunch of data set with the coordinates. By just looking at these, it's extremely difficult to see how many clusters, right? We don't know, like by just looking at this, we are not able to imagine like there's 2 groups or 3 groups or 4 groups, right? That's the challenge that we have. Second challenge is, suppose we have how many groups, but how are we gonna group them together? That's the second question second challenge that we have to tackle it, right? That's the big issues in clustering or unsupervised learnings, and we're gonna go through one by one. Now, I guess here in this slide is we start with supervised learnings and unsupervised learnings. And when you're talking about the groupings, it is clustering, classifications, and the other side is we have clusterings. And I hope that you have clear understanding of those differences. Now, because you all know the classifications, now let's talk about clustering. Data clustering is unsupervised learning problems, like I said in the previous slide. So let's formalize the data clustering in more like strict or mathematical way with the expressions. And the given, we have n number of unlabeled examples or data points, which means that only inputs is available. Right, that's what. And the second condition we have this, we have to know the number of partitions, like number of groups or number of clusters. That's weird, right? So we have to find out, because in the thing that I mentioned in the previous slides is that over there's no way we can know the number of partitions ahead. But here it says is we have to know number of partitions k. Let's suppose at this moment we know the k. Suppose, right? I mean, in real problems we don't know. I agree that, but at this moment, suppose we know the number of partitions. It's k. Okay, I'm gonna revisit to find out the case, but at this moment, suppose we know our number of partitions k is given, right? So that's kind of tricky part at this moment. And with these 2 given conditions, and the goal is that group the examples or data points into k partitions, right? That's the obvious, that's the purpose of clusterings. Like I said, with these examples that we have here, kind of we assume that, okay, let's do clusterings. And probably the way that I want is that, I mean, suppose we are visualizing, then these will be one partitions or one cluster, and these gonna be another clusters. It's a natural way, but again, in these, like, if you put it the data points with the coordinates, it's not easy. It's not intuitive, at least for computers. And let's think about more in how you're gonna cluster them. Then we have to come up with, like you can see in the title, is similarities. Similarities. The basic idea is that the only information clustering use is that mutual similarity between samples. Mutual similarity between. There are many ways that we can define the similarities, but the conceptual way is that, okay, so good clustering, we don't know what good clustering is, but I guess is it's reasonable that one that achieves, okay, within cluster high similarities. So like here, each data point should be has very high similarities because it's in the same partition. Intercluster, like here, one data points from here, the other points from the other cluster, has low similarities or dissimilarities. Does it make sense, right? I think it makes sense. So within the same partitions, within the same cluster, within the same groups, it should be like very similar to each other. When in other clusters, it doesn't have to be, or it should be different. Then the question is, how can you define the definition of similarity? There are so many ways that we can define the similarities. But in this slide that I want to say is that conceptual why. We don't know what similarity is. We don't know how to compute it. We don't know, but at least if we suppose that we find some good clusters, then the outcome should be like satisfy these conditions. So there are many ways that we can solve, but I'm going to give you the answer first. There are many ways that we can tackle clustering, but one of the famous one is that k-means. So I'm gonna give you the answer first. Then let's see why this k-means. This gonna see that we go through the k-means, why this makes sense, right? So in this here in the clustering, I'm gonna have different approaches. I'm going to show you the kind of right answers. I mean, one of the right answers. Then let's see whether this makes sense or not. And here in the title, I said that iterative. I'm gonna show you why I put the iterative there. And I mean, again, I'm going to give you the answer first. So initializations. Since the input is that we know the k number of clusters and we do have training data set input only. So this is the training data set. And since we know the number of clusters, I guess here 2 clusters, randomly initialize the cluster centers. Let's say just put 2 numbers, random initializations. Okay. At the first iterations, or we call it is random initializations. Of course, it's randomly assigned, so it's, I mean, doesn't have to be the answers. That's okay. So I guess this one is the center of one cluster, and this one is another center for another cluster. The second step is that now we can compute the similarities. One of the definitions of similarity they can use is distance. If they're close enough, very similar. If far away, it's not similar. So I guess, say this data point, for instance, we can compute the distance. I guess this data point is closer to the red, the center, so it's high similarity, so that I can assign that this data point should be part of the red, right? Part of the red cluster. We can compute the distance, right, from any data points to the randomly initialized centers. And we can compute the distance, or we say we can compute the similarity. Then we can assign whether this is red belongs to red or belongs to blue. So I guess, I mean, in that case, it's probably like, so we can, that's how we So now I can assign all the training data points. I can assign it is red and blue. Of course, it's not the right answers because it's randomly initialized. Now we have two clusters. One is red, the other one is blue. It doesn't have the answers, doesn't have to be the answers, but at least we have, for training data set, we put different colors on it, which is good. Now we can update these data points. We can compute the center, like a center of mass. Okay, now for blues, we can do that again. Now we can, based on these, we can update the centers of two clusters. Does it make sense? Now, since we have two different, now the centers are updated. That with that updated centers, we can compute the distance, or we can compute the similarity again. Then the partitions or groupings or clusterings might be different. So for each training data points, the colors might be different. So with the updated colors, we can recompute center of mass again. That's why we call it, it's iterative. So the thing is that we're going to repeat that process until convergence. Okay. If you got converge something, that means the cluster centers does not change anymore. Okay, but don't forget that this is like heuristic way, so doesn't have to converge into some. So it does not guarantee the convergence, but it's okay. It's okay. All right. So it's not guaranteed that, but I'm gonna revisit that point again in a minute. But at least you can, I think it makes sense to you guys as well. Okay, that's k-means. Now you guys have to understand what k comes from, because we have to assume the number of partitions, and means means whenever we updated the center of a mass, we have to take the average of we have to take the mean. That's why the name is k-means. All right, now I hope that you understand what k-means named after. So the output is that now, I mean, if you repeat that process, like there, red and blues, and these are the center of mass or center of clusters. And as you can see right there, I mean, remember that it's unsupervised learnings. We do not have any labeled data set at the beginning. Now, as you can see over there, we got something, and I guess the result out of k-means, at least in this case, it makes sense. And that's exactly what we want. Now I'm gonna do the same thing. I'm gonna repeat that explanations with this kind of animation pictorial examples. Okay, so starting from green, the data points, which means that it's unsupervised learnings, and suppose the k is equal to 2 that's given, and with the random initializations in blue and red, right? Compute the similarities and recolorings. So we assigned each group, each clusters, but of course that's not we know that this is not correct, but with that we can update it to center of mass or center of clusters, and with that updated, that we can recompute the similarities. Now we put different colors on it. Now just look at the center, it's moved. And repeat that process, moved. Repeat that process, moved. And eventually, this is how we got. That's clusterings. That's clusterings. K means clusterings. Okay. I mean, okay, I guess after the explanations, probably K means is like nothing special, nothing special. But put your shoes on, like you say that you have to come up with some method for clusterings. It's not easy to have that kind of things. Okay. So summary for K means clusterings. Again, it's iterative. So randomly initialize K cluster centroid. That's the center of mass, center of clusters, and we have K's. And repeat that. So the first step is that pick the closest one. So we assign it, since we have K clusters, we have to assign them. Then each clusters, we take the average or mean of that. Then we update it centroid. Repeat these. So that's K-means. Okay, I'm done with the K-means, but there are many lessons that we can think of or we can learn from the K-means. Okay, and there's some expectation maximization algorithm, EM algorithms, and names probably just, I mean, it's important, but at this moment you don't need to know. You don't need to know what's the EM algorithms here, but there are some things that I want to discuss, and there is something that I want you guys to think of. So it's clusterings. It's same as chicken and egg problems. Chicken and egg problems. Which one comes first, chicken or egg? What do you mean by that? Is that, okay, someone is gonna ask, if you knew CIs, means that if you know like the colors, how do I say, for each data points, say if you know, let's say we have to put different colors for clusterings, then how is determine which point is to associate with each cluster centers. Then for each data points, we can compute the similarity or distance and pick the closest one. Okay. And another guy is going to ask, if we knew the cluster memberships, then how are you going to get the centers? We can compute it. We can choose the centers means of all the points in that cluster. I mean, though I go back to here, the question is that if we know the centers, centroid, then for each point we can associate each cluster centers. Pick the closest one. But the question is to choose the closest one, we have to know centers, but we don't know. And to to take the mean of all points in the cluster, we have to know the cluster membership, but we don't know. We don't know. So that's the dilemma that we have. This one is kind of, so let's say if A is done, suppose we can do B's. A and B, it doesn't matter anything. But if B is done or given, say we can do A. There are two people trying to work together. The person one say that if A is given, I can make B. But the other person say that if B is given, I can make A. Right? But the problem is A and B is not done. So nothing happened. Nothing happened. Nothing happened. That's the chicken and egg problems or issues or dilemmas that we have. Okay. In that case, what K means, the philosophy of K means, this means that if we know the true A's, then we can make true B's. If we know true B's, we can make true A's. But since we don't have true A's, I cannot do anything for B's. Since we don't have any true B's, we cannot do anything for A's. In that case, do it. Just do it. Do anything. Since this is the first time, probably A is not correct, but it's okay. Randomly initialize it. We know that this is not true, but since now, although A is not correct, now we do have A primes, then we can do B primes, right? Now we have B primes. Since we have B primes, now we can do A double primes. This guy can do something. Now this means that from A primes, now is A double primes. It's updated. Now since it's updated one, we can do, and I can update it again. Now this is iterative way. So in philosophy, what I have is that for chicken and egg problems, starting from like randomly initialized something. In that, of course, in the first iterations, but if you repeat that process, hoping that the answer is going to converge to true answers. That's better than doing nothing. That's better than doing nothing. That's the idea of K-means, or idea of expectation maximization algorithm. Okay, I hope that you learn some big lessons from that. Okay, so for example, it might be different, but say you have, as a students, probably you want to have teamwork. I said there's some kind of the class project you have. Then what the K means, the lesson that from the K means is that do something. But the idea is that repeat that. Okay, don't try to make the good product in the first iterations, and do not think too much. Just do it, even though that might be the true answers, but do something, and with that, do continuous improvement. That's the key. You have to do continuous improvement. You have to improve continuously. Okay, that's kind of aside from the k-means, but I guess that's kind of the lesson that we can learn from k-means. Okay, so I'm done with explaining what k-means is that. Of course, we have to implement it in Python. So in order to do that, we just start from the data generations and you use that now, and you can see that there's kind of 3 groups or 3 partitions. Suppose k is equal to 3. Now, like I said, k should be given, although it's not realistic, but assume that it's okay because I'm going to revisit again that point. Now, the random initializations now have 3 centroid. Based on this, based on this, like we run the k-means. Over there is, I just said it's run 500 times, but this is, it's actually, you have to have some kind of stopping criteria. Say that is the centroid, if the stop it when centroid doesn't, centroid do not change anymore or do not update anymore. But for just simplicity, I said it's repeated that 500 times. That's the, and here we compute the distance or similarities and pick the closest to 1. Okay, we assign that, and among that, like here, that is take the mean. That means I have to I'm updating uCentroid. Okay, and repeat that. Now at the end, we got, at least from here, because since it's 2-dimensional space, we can plot and can visualize, and I guess we did it correctly. Again, it should be in scikit-learns, so it's sklearns and k-means, and we have to give number of k, of course, and fit. That's it. That's it. And it's extremely easy to implement or use. Okay. But like I said, there are some issues on that. So k-means, like I said, we're starting from random initializations. So of course, it's extremely sensitive to cluster center initializations, right? So if you have good enough, lucky enough, probably we're gonna have at the end, because doing the iteration process, we'll get good clusters. But if you it's bad luck, probably not. So bad initializations might lead to poor convergence speed or bad overall clustering, like I said. How I'm gonna avoid or overcome such kind of issues? Any ideas? Actually, in practical sense, it says try multiple times. Multiple initializations, choose the best result. All right. We're just gonna ask computers to do multiple trials. So it's for multiple trials for computers, that's extremely easy. Extremely easy. So I guess this one is like, in a practical sense, is extremely useful. Or say choose the first center as one of the examples, because you just pick one of them. And the second, which is the farthest from the first. And third, which is the farthest from the both. It's kind of like just put the centroid as far away from each other. That's kind of one trick. We can try that, but I guess this one is easy and better. Now this is the right moments that you have now, is we have to think about it, because in k-means that I said is number of k is given. for me, it doesn't make sense at all. So now we have to choose the number of clusters. Now K is not known in advance. So any ideas? Any ideas? So the idea is that when adding another cluster does not give much better modeling of the data. Okay, so suppose we have two groups. And maybe these two at probably is right number of K. And if we have only one, probably the performance, if there are some scores or metrics that we can define how good cluster is, probably this one is bad. And I guess this one is the best. I mean, this is good. But if we have add one more, say is K is equal to 3. Okay. So if we add more, add number of clusters, the performance is always it's getting better and better. And I'm going to explain these things in the following slide. So choosing the number of clusters, we have to say that for K means starting from 1 to 10. This is K. And I computed how do I compute it? Say it is that, so you have the data points right there. And if it's 1 is, that means we have one cluster. That means probably this one is the centroid, and I can compute all the distance. That's probably like that. And when K is 2, now probably I do have these two centroid. Then I can compute the distance within the same cluster memberships. And over there, they're probably that one. Okay. And if this is add another one, probably like there's some data is belongs to third, and these will be the sum of the distance. So like I said, it gets better and gets better. And say we have like 200 data points. When K is 200, then the error summation of error is equal to zeros, right? Because we can assign centroid for each training data points. So eventually the metric over there is going to be zeros. So if we add more Ks, the performance gets better and better. But the idea is that if you say from 1 to 2, the improvement is huge. But since we know the K is equal to 2 in this case, if we add one more, the improvement is not that significant. Not that significant. Like here. I mean, from here. Let me show you. We start from, I guess here is, I'm not sure exactly, but I guess it's this is the case. So we call it improvement, and it's not significant. So probably I'm gonna say the right K is equal to 3. So we call it, it looks like this is like elbow, like over there. All right, it's a kind of elbow point. So we call it elbow point. Just look for the elbow point. Another lesson that we can learn from here is that, okay, say at the beginning, given clustering problems, the first thing is that we have to know number of Ks. Otherwise, we cannot do anything. But we don't know Ks. In that case, think about it. Assume that we know K. Assume that we know K. Then just doing following like logical process to solve that clustering problems. Once we set that method, using that method, like you can see in the slide, we have kind of way that we can figure out the K. Okay. So whenever you have your like research problems, whatever, and say you have to know this one, but there's no way that we can do all with the knowledge that we have at this moment, in that case, don't give up. Just assume that you know the answers, although you don't know. Then with that assumptions, continue your discussions and think about, but somehow once you're done with that, there's a way that you can figure out the case, or the assumption at the beginning, the assumption that you assume that you know, right? For me, it's when I learn K-means, it kind of have big impact or influence that the way that I'm thinking of engineering problems. Okay? That's the actually, I mean, K-means probably you just, it's not that easy, so you guys easily understand, and I mean, you can implement it and you can solve many clustering problems and machine learning problems. I mean, this is top priority. But the second thing is that I want you guys learn something, kind of the philosophies that we can learn from K-means. Okay? But another thing is that K-means is not perfect. There's some limitations. There's limitations. Make hard assignment of points to what do you mean by hard assignment? Say that I said for each training data point, we have to put different colors on it. That means this one like red and this one is blue. Okay, a point either completely belongs to cluster or not belongs to error. Right? And here hard assignment and soft assignment. Probably we can say, I can say probabilities of being assigned to each cluster. For instance, this data point or training data set is like say have 80% of being assigned to the first class and 20% of being assigned to second, the first cluster and 20% of being assigned to second cluster. Okay, that's so actually the K-means is hard assignment and it's one of the or extreme case of soft assignment. Okay. So that's another thing that I want to mention. But don't worry about this, is out of the scope for this class. So for clusterings, only algorithm that I want to cover in this lecture is K-means. And another issue is extremely sensitive outliers. Is sensitive outliers. Okay. And it works where only rounded shape, roughly equal size and density cluster. What it means, since we have, the reason why is that I'm going to show you this one, this example as well. And with this, we're hoping that this kind of clusters, I mean, this I'm showing this one is the result of clusterings, and with these data points, this is kind of the we expected it. But from k-means, probably you're gonna get this kind of. Why? Because think about the definition of similarity is you use the Euclidean distance. Euclidean distance. That's why it's for rounded shape or for convex. But as you can see there, these data points from is much closer, which is far away. But we know that it looks like these are connected, and these are connected. So for k-means, we did not, it does not count into account the connectivities. It's only count of the distance as a function or definition of the similarities. Okay, so that's weak point. That's weak point. So the connectivity is one of the important things for clusterings, but for k-means, at least for k-means, they do not consider the connectivities. And there is another way that we can overcome the issues, but again, this is out of the scope. So for connectivities using network theories and especially it's a spectral partitionings, right? Just remember that, and this is extremely useful to compute the connectivities and for clusterings as well, but I'm not going to cover it. Go back to here. So again, it's better if the cluster have non-convex shape, with same reasons, because the similarity definition that we use is Euclidean distance. It's rounded shapes or convex. That's the problem. Okay, so that's all I have for clusterings. And again, start from the unsupervised learnings. This is first time that we covered unsupervised learnings in these lectures in this semester. And the only difference is that the data set that we have is not labeled. So in general, unsupervised learning is difficult. It's more difficult than supervised learnings. I mean, in general. And the clustering is part of the unsupervised learnings. And I show you the definitions. I show you that you have to understand the difference between classifications and clusterings. And there are many algorithms to cover the clusters, but I showed you only one, which is k-means. K-means. It's iterative way, so we have to start with random initializations. We update the centroid and repeat. That's the key ideas. But there are several lessons that we use. One of them is chicken and egg problems and EM algorithms. And second thing is that how do you find the case? K is elbow point. We assume that we know K. And we kind of done with the theory. And we're using that theory that we can revisit to find out or figure out the good case. Right? That's the ideas. And I end up with some of the limitations that we have. Okay, that's all I have for clusterings, and I'm gonna stop the lectures right here.